In our last class, we discussed about the pH, acid, base. Today we are going to continue there. But first, let's do this problem. Can you all do that? You learned it in 10 cam. Can you all do that? Huh? Okay? Okay, so how are you going to do it? Here I am asking, calculate the hydrogen ion concentration. That means this thing. Hydrogen ion concentration for a tomato juice. Tomato juice has a pH of 4.30 at 25 degrees Celsius. What is the equation are you going to use?
pH equals -1.
Yeah, pH equals, tell me,
-1
log,
of the H plus ion.
then H plus ion, correct?
Yes.
The reason we are using this one is because we have only one thing, tomato juice, nothing else. So this is the one thing that we are adding. We are trying to measure the pH. So we already have the pH. We are trying to measure this one, right? So the way you do it is just an anti-log, like you do normally the books they draw it like that. So here you write it like that, H plus. So basically you write H plus, and then because you are taking the log on the other side, it becomes 10, a negative of pH. Now you need to know how you use it in the calculators. Okay, in your calculator, how do you calculate it? So this is very easy. Just put the pH value, which is 4.30, and you should get. So try it for each of you. Try your calculator to get this value from here. All right. So you should get 5.01 times 10, -5. This is the concentration, right? So molarity is the concentration unit. You need to write the unit. Yeah? Yeah, so you when you solve this with your calculator, you are gonna get this value. Okay? Now, if you ask me how to show you the calculator, please come to my office because each calculator is different. Okay? I may not be able to do it now. So, but you should, if you have any problem, there are tutors. You know that there is a tutor for chemistry. I think I sent an email about that on Blackboard. So they should be able to help you if you don't know how to do that.
That's reason.
Okay?
And that's it for chemistry.
Any question? Okay. Alright, so this is how we calculate the pH. Any question about this one? Everyone fine? Okay. Now we know the pH and the acid and base definition. Calculating the concentration of hydrogen ion. Now you are going to focus on two things. One is a strong acid and a strong base. Okay, weak acid and weak base. We discussed that. How many strong acids are there? Can you name it? We asked that in our last class. Hydrochloric acid, hydrobromic, hydroiodic, sulfuric, one more remaining. Nitric acid. Okay, nitric acid. If you see any other acid, you just consider their weak acid. Okay? So the acids that we just discussed are like this. Hydrochloric acid, these are a strong acid, okay? Strong. HBr, HI, hydroiodic acid, then H, HNO3. This is called nitric acid, and the other one is sulfuric acid. So at least you remember this 1, 2, 3, 4, 5 of them. Okay. There is one more, hypochlorite chlorous acid, something like that, forget about that. We are not doing Gen Chem, okay? But at least these 5 you remember. Can you remember this? So I'm writing it now. Please make sure you know that. All right. Then what is weak acid?
Everything else.
All except these ones. Okay? Just consider that like that. All right. Now we are talking about a strong acid. What is a strong acid? Look at this picture. Picture says a lot of things, right? If you don't believe it, show the picture. People say it, right? Show the evidence. I need a video clip or I need a picture to show something, right? That's what we do. Look at here. Hydrochloric acid is a strong acid. We discussed that. We write it there, right? Hydrochloric acid. Look what is happening. In water, because hydrochloric acid is in water, that's why we call it aqueous solution of hydrochloric acid. They dissolve completely and form chloride and hydronium ion. That means here I am showing that this reaction. Actually, I can write it here if it helps. HCl plus water, because you are adding with water, gives H3O plus and Cl minus. Okay? Look at here. This is a strong acid. It's strong. So it dissociates completely. So what is it? Dissociates completely and form these two. Okay? You don't see anything like that remaining HCl. Dissociates completely. If a molecule dissociates completely, if an acid dissociates completely, it's a strong acid. I mean, it dissociates completely, complete. Dissociation. Okay? And that's why we are writing in this sign, symbol, arrow. It's going all the way here. Okay? So you see all are chloride and hydronium ion. What is this acid? Weak or strong?
Weak.
Weak. This is not one of them, right?
Mm.
So sometimes we think that hydrofluoric acid should be very strong acid. No, no, no. Why no? Can anybody tell me? What is the definition of weak and strong acid? Or what is the strong acid? The molecule that, the acid that dissociates completely, right? A strong acid means the acid that dissociates completely.
Mm.
Hydrofluoric acid doesn't dissociate completely. That's why it is a weak acid. Okay? So now if this happens, if it doesn't dissociate, what is gonna happen? You are gonna get HF, just like write equation like this, plus water. Right now I'm gonna write it like that, but I will change it. And F minus. But the problem is, you know fluorine is on the first row in the periodic table. This negative charge likes the positive charge a lot, right? So it wants to go back and form this one again. That's the reason why hydrofluoric acid is not a strong acid. The definition was that strong acid means it has to dissociate. Hydrofluoric acid doesn't dissociate because once it forms this thing, this negative charge wants to add a positive charge because it is very strong. It likes to have a positive charge more than chloride, bromide, iodide, all those things. So it doesn't dissociate. What it does is once it forms like that, it again goes back. You understand what I'm saying? So it doesn't dissociate completely. How do I say? Doesn't dissociate. How do I write it? Like this, right? Dissociate completely. In fact, it stays like that most of the time. Once it forms like that, this F likes the proton from here. So what it does, it forms water and H plus, right? H plus goes there and it forms this thing back. Right, guys? Any question? So this is weak acid. Now look at this picture. Most of them are hydrofluoric acid. You see hydrofluoric acid. You see only a few of them. So that's why it is a weak acid. Got it? All right. There are other pictures. Same thing I'm showing in a different way. You see, this is complete dissociation. That's why HA, which is the acid, breaks, dissociates, forms these two. Okay, these two are the products. Okay, this is a strong acid. If I now show the weak acid, look, HA stays as HA. You get a very small amount of A minus and H3O. Everyone got it? Any question? All right. So this is a strong acid and a strong base. Okay. Now in our last class we discussed about acid dissociation constant. You can write it either like this way or this way, it doesn't matter. But if I give you this one, this equation, you have to write the acid dissociation constant in this form. Ka equals product this times this over this. Okay? It's called acid dissociation constant. Now we are learning that if the Ka value is high, it's going to be a strong acid. Can anybody tell me why it is a strong acid? If Ka value is high in terms of concentration? Yes.
So if there's more product, it's dissociating a lot more. So if you have more product, then there's going to be a higher acid, a higher Ka value.
Ka value, exactly. That means if it is a strong acid, you are going to get this one, these two more, right? That means concentration of these two will be more. So these two will be a lot, right? These two, you're multiplying this with this. These are already high, and again you are multiplying them. So this number after multiplication gets really big, right? Compared to this one. So when you divide a big number with a small number, Ka value gets bigger, right? Let's say 10 over 2, it's a 5, right? But if you have a weak acid, it's going to be, let's say, 2 over 2, it's going to be 1. So this is a strong acid. For a strong acid, this is for a weak acid. So this is the math behind it. This is the math we are trying to understand in terms of quantitatively. This is now quantitatively we are understanding. So if I give you a Ka value, if I give you two Ka values for weak acids, you can now say which weak acid is the stronger one, correct? So that's why I'm giving you, let's say 1 Ka value is, you have two acids, let's say you have two acids. One is HF, let me not give you the name. Let's say this is weak acid 1, this is weak acid 2. For this one, Ka is 3 times 10 negative 7. For this one, Ka equals 3 times 10 negative 2. Which one is the stronger one between these two? Everyone got it? Everyone understand what is the big one? Tell me. There is the reason why I'm putting negative 7 and negative 2. Which one is the bigger one? This one or this one? This one, because this one has less This negative 2 is smaller. This one is 7. So that means it is even bigger. Like how do I say it is smaller, okay? So this is smaller than this one. So this one is going to be comparably between the two. This one is stronger. This is the weaker one. Got it? Any question? All right. So we learned about acid and weak acid, strong acid. Now we are trying to learn titration. Can anybody tell me what is titration? Have you done titration before? How many of you have done titration before? 1, 2, 3, 4, 5, 6, 7, 8. Only 8 of you? Have you done titration, guys? Okay, so you guys have done titration. So titration is nothing but you see this is the setup. What is this thing? It's a burette. This is in this case I'm using a beaker. Okay? This is the holder of the beaker, burette. Here normally we keep the base. Here we use the acid, and here we have the base. So the titration is like you are trying to neutralize. Normally what we do in titration is we try to neutralize the solution. If you have a acid here, we use sodium hydroxide or any base to neutralize this solution. So when you neutralize the solution from acid to with the base, what happens with the pH? Increase or decrease? Increase, correct? Because here you have a acid that has a pH, let's say it's around 2 or 3. When you add sodium hydroxide, the pH is, this is a HCl, let's say this is HCl. Let's put it 2. And this one is sodium hydroxide, which is here. It is around 13. So you are titrating acid with base. So you need to know the volume, how much base you are adding, and you need to put some amount of acid, let's say 25 milliliters. And here you are adding sodium hydroxide. So you are adding enough sodium hydroxide so that you can neutralize the acid. So slowly you are adding sodium hydroxide. What happens? Since you are adding with the sodium hydroxide, pH is going to increase. Okay? So after adding, let's say about 15 or 20 or 15 milliliters of sodium hydroxide, you reached around 7 pH. So now you know how much sodium hydroxide you added to make it pH neutral. If you already know the concentration, of sodium hydroxide, you can calculate the concentration of hydrochloric acid with the titration. Okay? So if you know the concentration of sodium hydroxide, let's say this is 0.1 molar. You don't know the concentration of hydrochloric acid, you don't know that. And you know the hydrochloric acid you added is around 25 milliliters. Now that you have this value, and this value, you can calculate the concentration of hydrochloric acid. How? We normally use C1, V1 equals C2, V2. Now, I'm not making it complicated. If you have sulfuric acid, then this formula doesn't work. Because sulfuric acid has 2 hydrogens. So, if this is the unknown for hydrochloric acid, you can calculate the concentration of hydrochloric acid in this way. So C1 is gonna be 0.1, right? V1 is 15. Divided by V2 is 25. And now you calculate the C2. This is the concentration of hydrochloric acid. Any question about that? I know I'm not explaining that in detail because I think more or less you heard of that, right? You have done that. So I'm trying to go slowly, quickly, so that we can use the titration for amino acids. All right?
Mm.
So you see, we are measuring the concentration of C2. Now, same way you can add acetic acid, which is a weak acid, and you are adding sodium hydroxide, and at pH 4.76, you see at this region here pH is this. Now the thing is, if you look at this picture, 50% of the acid is dissociated to acetic acid. Sorry, acetic acid is dissociated to acetate, 50% at this point, and the pH is 4.76. This is called, and this happens at the value of Ka, pKa. Okay, pKa. So we are gonna let me explain it again. Everybody wrote this one? All right. All right. So let's write the equation for acetic acid. CH3COOH in water giving CH3COO minus. Okay? So, and H plus is coming like that. So this is the equation for this. Now if you are adding sodium hydroxide to a acid, what happens? This reacts with sodium hydroxide, and hydroxide is giving, sodium hydroxide is giving sodium plus and OH minus. And that's the reason why we have hydroxide here, okay? Hydroxide. So what happens? Hydroxide, can anybody tell me, this hydroxide reacts with which one? This one or this one? This one. So now CH3COOH OH gives CH3COO minus and water, right? So this is the titration we are doing now. You are adding sodium hydroxide, acid is reacting with sodium hydroxide, and you are getting this and this. As you add hydroxide with the titration, you are adding more and more. What happens? At one point, initially you had this one a lot. When you just start the reaction, at the start of the reaction, you have this one a lot. Okay? But after, when you are adding hydroxide, as you add hydroxide, this thing decreases. And this thing is, initially it was very low or almost none, and then it is increasing. All right? So what is going on? You are adding sodium hydroxide. This is reacting. Since it is reacting, it is forming this, and with the some penalty. When it forms this, that means you are losing this one, right? This is a reaction. If you form this, that means you are losing some of this. So concentration of this decrease, and this one is increasing. So initially it was a lot, and it was very low. At one point, when the equilibrium, when you have added and at certain concentration of hydroxide, these two becomes equal. Equals. This two becomes equals. Okay? Because you are losing this one and you are making this one. Let's say you are started with 10 molar. A lot means, let's say you have 5 molar or something. Let's say you have a lot of this one, and you have very low of this. At one point, you will have both of them same concentration, let's say 5 and 5. And this is the time when you calculate the pH, when the concentration have this equal amount of this and this, the pH is going to be equal to pKa. This is very important. This is what we are going to have. You are going to have, some of you are going to have issues or problem understanding this when we discuss amino acids. When the two concentrations becomes equal, pH becomes equals to pKa. pKa and pH becomes same. Okay? Because by definition, Ka has to be equal to this. Yes?
Can you repeat that?
So when the concentration of acid and its conjugate base is same, then if you measure pH, the value the pH shows is actually the pKa, Okay? So let's say this pH over there they are showing 4.76. 4.76 is actually the pKa. Because pH changes, right? We discussed that pH changes. pH goes from, for acetic acid, when you started, the pH, let's say pH was 2.5 when you started. Then you were adding sodium hydroxide, pH is increasing, right? Increasing, and then when these two equals, then the pH becomes 4.76. Since these two are equal, it satisfies the equilibrium constant. Okay? So like the concentration equals, so it is called Ka, pKa. Alright? There is a reason why I am showing all this. Because we are going to talk with amino acids, okay? Amino acids. Amino acids undergoes this protonation, deprotonation. Alright? So this is a deprotonation. You see this thing is loose. You are losing the proton from the acid. Okay, so this is titration. And there is another point. So titration, you experiment measure the base and add to the acid. This is one. Equivalence point. Point in an acid-base titration at which enough base has been added to neutralize the acid. So when you neutralize the acid, that means the pH is 7. Then we get the equivalence point. Okay? That's called equivalence point. Okay. Now we are going to talk about buffer solution. What is a buffer solution? Can anybody tell me? Especially from my lab, we discuss buffer. What is a buffer solution? Huh? Yes.
A solution that resists change in its pH.
Yeah. So the solution that resistant change in pH. Can anybody tell me what an example? An example of a buffer solution. Yes.
Blood.
Huh?
Blood.
Blood is a buffer solution, but yeah, you are good. But what is the ingredient? And what are the? Can you give me one of the chemical compound in blood that is buffer solution? That is making the blood buffer. Huh? Yes. Sodium acetate is not in blood actually, but it can make a buffer solution. Huh? No. Have you heard of an acid that prevents snakes to come inside the house? Have you heard of that? So if a snake doesn't like one kind of chemical compound.
Carbonate?
Yeah, someone is saying something.
Carbonate?
Carbonic acid. Carbonic acid, snakes doesn't like. So if you have, although I am not totally 100% sure if it works for all the snakes or not, But if you go to some place where you see a lot of snakes, and you are afraid to sleep at night, keep some carbonic acid in your bed, under your bed. Hopefully the snakes are not gonna come. Okay? So carbonic acid. We have carbonic acid in our blood. H2CO3. H2CO3. In the activity, we have it today. This is the one. H2CO3. This is called carbonic acid. Okay? This thing is called carbonate. This thing is called carbonate. But this whole thing is called carbonic acid. So, okay, we'll talk about this later. First, let's finish the buffer. So, buffer solution change doesn't allow the change in pH. So, let me show you one thing very, very quickly. Look at this picture. We have hydrochloric acid here. Okay? It is a dilute solution, so pH is high. Okay, it is dilute, so pH is high. We are adding, next picture. So here you see, we have added, in this case, we have added concentrated solution of hydrochloric acid. Now it is concentrated 1 molar, right? So what we did, we have concentrated solution of hydrochloric acid and we have sodium hydroxide. Now, this is our initial acid. We are adding concentrated solution of acid in this solution. What happens? pH decreased. You see the picture? We have a smaller amount. Now we added some from here to this solution. This is the new solution. Now you measure the pH. It is 2. Because it is acid, a strong acid. You are adding a strong acid to this solution. Okay? So pH decreased by how much? From 5 to 2, about 3 pH. Similarly, you are adding now sodium hydroxide to this beaker. Sodium hydroxide is 1 molar sodium hydroxide you added, which is a strong base. The pH increased to 12. So all of a sudden from 5 to 12, a big change, right, in the pH. Everyone all right? From this side, you get it? Everyone? All right, so this is not a buffer solution. Buffer solution resists change in pH, right? But this one is not a buffer solution. It doesn't resist change in pH. It is changing the pHs when you added a strong acid and a strong base. Now we take a buffer solution. You see that this is the buffer solution. Again, the pH is 5. Now we are adding a strong acid and a strong base. Look at the change. It was 5 after adding a strong hydrochloric acid solution. You get 4.98. Very, very tiny change, right? Similarly, it is very, very tiny change here too after adding sodium hydroxide. So this is why we call buffer solution. It resists change in pH. Got it? All right. Now, how do you make a buffer solution? We discussed that in a mind lab. I don't know, is Dr. Kelly showing those things? No?
It's easy, I lost this.
Okay. Okay, so buffer solution. I gave him all my course schedule. Anyway, so this is a buffer solution. You make buffer solution by adding a acid and its conjugate base. All right? Or a base with its conjugate acid. In our last class, in my lab, I showed how you make it. So if you have, let me show you. So you have a weak acid, you take, let's say, 10 milliliters of, you take 10 milliliters of 0.1 molar acetic acid. Okay? Your beaker is here. Just like over there, they are writing weak acid, I am just saying more. You added 10 milliliters here, okay? 10 milliliters. But to make buffer, this is an acid, weak acid. This is not a buffer solution. To make a buffer solution, you have to add its conjugate base. In the buffer solution, okay, let's try to understand again about weak acid. What happens with this weak acid? Can you show me? What happens? Weak acid means what? It doesn't distillate completely, correct?
Right.
So what happens? What are you gonna get in this solution? Are you gonna get this one, or are you gonna get a lot of other things? What is the equation for an acid? Can you tell me? With water, how does it react?
Maybe CH3CO minus.
How does it react? Can anybody tell me? Just like acid reaction, acid with water, what does it form?
The hydrogen.
Hydrogen ion or hydronium ion, and
CH3CO.
in this case it is CH3 COO minus, correct?
Yeah.
Now you tell me in this solution, what item is gonna be a lot? Because it's a weak acid.
It's gonna go back and forth.
Yeah, but which one is gonna be the highest amount, the concentration
The one
wise?
on the left.
The left on this one, right? You are gonna have a lot of this, right? So this solution will have a lot of CH3 COOH, correct? We just discussed that a few minutes ago. You have only one or two of these. Most of them are HF, 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 HF. Okay? So most of them are acetic acid. Like same here. Most of them are acetic acid, HA. But to make a buffer solution, what do you need? You also need its so you need acid, a weak acid, and conjugate base. This is what you need to make a buffer solution. What else you need? The concentration of weak acid must be very similar, must be almost equal to the concentration of conjugate base. But in this solution, we have mostly this one. We don't have conjugate base, right? So now you have to make the buffer solution, you have to add conjugate base. But the problem is, how are you going to add this thing? This is an ion. You cannot get it like this way, right? So you have to add, now you have to add, so this is what you need to make a buffer solution, to make a buffer solution. Alright? You need number one, this thing. Number two, you need is what? This one, but this one is naturally you cannot get it because it's an ion. You can get a salt of it. So sodium acetate, CH3 COO and Na, or you can also write it in the beginning. NaCH3COO. This is called the salt of acetic acid, acetate, sodium acetate salt. This is, as soon as you put it in the solution, because it has water in it, it is gonna form sodium plus and CH3COO minus. This is the aqueous solution. In aqueous solution, this is the aqueous solution. In aqueous solution, in the water, aqueous means in water. In water, they make this. So as soon as you, so now you add what I just said, sodium acetate. You are gonna get like that amount, and you are gonna have, now you are gonna have CH3COO minus. Sodium is also gonna be there, sodium plus, but we don't care, it doesn't react with anything. So sodium is also there, but we don't care. So now you have equal amount of this and this. Try to make equal amount of this and this. That means CH3COOH equals CH3COO minus, concentration are equal in this solution. So now you get the buffer solution. Got it, guys? Any question? Ask me. Ask me questions. Okay. What is this? I just told you.
Carbon?
Carbonic acid. All right, and it is the conjugate base of this carbonic acid. All right, and this is found in blood. So same way, I just explained all those here. No need to explain it again. All right, now let's do some problem. pH of a human blood is 7.4. One of the buffer in the body is carbonate. How does it regulate constant pH in the body? Can anybody write it? I'm giving you the formula of the acid. Can you tell me? Can you write the formula? Can you write in terms of acid and base? Without looking at it, can you write it like this? Everybody do that. Write the reaction. Yes?
Can I get an activity?
Yes. Anyone new? Just came, activity.
Okay, so these change.
Someone else, over here.
Oh, are you doing this? How do you?
Okay, I can see some of you have already written it. Very good. So the way it works is H2CO3 H2CO3. Tell me, guys, tell me how you are writing the equation. Then what? H2O, good, and then
H3O plus
this is the weak acid, so you have to write it like that. Okay, H3O plus, and then CO3 minus. Okay, this negative sign. This is the equation. Now, show the reaction. I said this is the reaction. Now, I will add a little bit of that. So now, can you tell me how does it regulate the constant pH in the body? So this is the equation. So when you add the buffer solution, because it's a buffer solution, you have a lot of this one and this one because it's a buffer solution. It's not the weak acid reaction, it is the buffer solution reaction, okay? You have this one as well as this one because it's a buffer solution now. Okay? So you have this and this. Now, how does it control the pH? If you add a strong acid, what happens? So if you add a strong acid, tell me guys, what does it, a strong acid gives what?
H.
H, proton, right? H plus, correct? Gives a lot of H plus, correct?
Mm-hmm.
So which one is gonna react with? This one or this one? On the left, on the right, sorry. So it's gonna give HCO3 minus reacts with this thing. H plus means H3O plus, okay? Gives this thing and forms H2CO3 plus H2O. The reason I'm using, instead of using proton, I'm using H3O plus because at the end I get the water. If I use the proton, I'm not going to get the water to have the reaction complete. Okay? So if you add a hydrochloric acid, it's not going to increase the pH because hydronium ion or H plus is going to react with this thing, forming this. They are weak acid, so weak acid doesn't increase the pH because you are mainly have this. You don't have, you are removing the proton. You are removing the proton. Removing the, you are removing this thing. So pH doesn't increase. Now if you add another one, if you add sodium hydroxide or a base, what happens?
Takes it.
Huh? Which one is it going to react with? Base gives what? Hydroxide. It reacts with, now base is going to react with what? H2CO3. H2CO3 reacts with base, gives what? HCO3 minus and water. You see, you are removing hydroxide from the body now, because otherwise it's gonna make the pH go high. So you are removing hydroxide. Any question? All right. Now, let's say we are talking, this is the answer for this question, but I'm gonna, if you want to now know more, in our body, what happens? The pH of the blood is what?
7.4.
It's around 7.4 to 7.3 to 4, okay? Now, if you have, these are weak acids and weak base, right? Weak, these are weak. You need the weak acid and weak conjugate base. These are weak. Now, if you are wondering, okay, how do we get this thing? Can you tell me? In our blood, H2CO3. Oxygen goes from our lung because we are taking the oxygen and it goes to the blood, right? Because hemoglobin is there. Similarly, after we are using the blood, we have used the oxygen, it releases carbon dioxide, right? So our lung also has carbon dioxide. So carbon dioxide reacts with water, forming this thing. Very good? And sometimes it also dissociates. This thing also dissociates and forms carbon dioxide and water. Okay? So if you have enough carbon dioxide, the reaction goes to this way. And if you have enough of this, then the reaction goes this way, carbon dioxide and water. It's a principle. What principle is it? Huh? There is a name with someone's name. If you have, let's say, you have a reaction like this. You add more carbon dioxide, reaction goes to this side, right? Because you have a lot of carbon dioxide. Similarly, if you have a lot of this, reaction goes on the left side, and form this too. It is due to Le Chatelier's principle. Le Chatelier's principle. Have you heard of that? Le Chatelier's principle. He or she heard of that? Le Chatelier's principle. Okay. So this is the Le Chatelier's principle. Now, what's the time now? I wanted to say.
It's 50.
Oh man. Okay. So just 1 second.
Oh my
Carbon
God.
dioxide reacts with water and form carbonic acid, right? So if you have a lot of carbon dioxide, if the reaction goes this way, sometimes carbon dioxide will release carbon dioxide and it goes away. Now, if you have a lot of hydronium ion, what happens? reaction goes on the left, and you form H2CO3, correct? So, in our body, sometimes we make, when we do exercises, it forms a lot of H3O plus, right?
Mhm.
So this H3O plus reacts and it's gonna form H2CO3.
Mhm.
It's a balance, all right? So if you form a lot of proton, since it's a buffer solution, H plus is gonna react with this and it's gonna form this, all right? And if you form this, and if it is a lot of this, then this is gonna go in this direction, form carbon dioxide and water. So extra carbon dioxide you are releasing.
Mhm.
So when you are exercise a lot, you are breathing more, right?
Mhm.
Because you are releasing the carbon dioxide from your body.
Mhm.
But if you stop breathing, you are actually getting more carbon dioxide in your body. So after 1 minute or something, you don't like, you are gonna die because it's not only that you feel bad, your body is also getting a lot of carbon dioxide in your body.
852.
Okay? Okay, that's it for today.